Hello, this talk is on direct estimation of SAGDable volumes from geologic models using oil sands net pay connectivity criteria for ranking and planning. And I want to just thank Sasan, my co-author, for providing a few extra slides for the talk. And this is part of our technical division talks. So here, let's acknowledge Emerson for providing some of the examples in some software. Geovariances for the geostatistical software used in some of these connectivity calculations and geostatistical calculations. And Basic FranLab for the software used for the Facies logs in the process here. So what is our agenda? I'll introduce the Athabasca oil sands very briefly. We'll review the SAGD type extraction. It's the base case technology. In the in-situ extraction, there are methods that people are using, and we'll cover the context for the geology, modeling, and what are the issues for these reservoirs. And then finally, the properties in the models. We'll cover facies, porosity, perm, saturation, and introduce bulk oil weight. We'll really be focused on perm and especially saturation. The connectivity within the reservoir is something that we will calculate given the SAGD concerns. And finally, we'll summarize uses of these connected estimates of the reservoir for volumetrics, linking it to dynamic behavior for forecasts and pad and well planning. In the Athabasca region, I'm going to turn off my picture there. So in the Athabasca region, we have Fort McMurray, and this is the Athabasca River just outside of Fort Mac in the early fall. And going by boat to see an outcrop. Here we walk along an outcrop, and the bitumen is quite spongy to walk on. It just oozes out of the rocks and basically, oozes into the river here. So the whole area is just saturated with bitumen. And so here's a nice picture from up on one of the outcrops looking out at the river. I've been there different times of the year. Here flying into one of the outcrops on the Christina River, and after we've walked down the outcrop looking back. So these are pretty big outcrops we can visit. And another interesting one, it's just trough cross-bedded sands sticking out of a rock face here on the Steep Bank River. So we have a lot of sand, channel sands, and whatnot. So I'm not showing you a map of the area. You can look that up if you like. So this is what the oil sands look like. We traditionally called it tar sands, and then some geochemists explained to us that it's actually the bitumen has a lot of different characteristics. It can be used for everything from jet fuel, diesel, gasoline. So there are a lot of different components in it. So it's not truly tar, but that's what we used to call it when I started working with this in the 90s. Okay, so SAGD is steam-assisted gravity drainage. This may be a review for some people, but I want to point out some issues and how we're going to evaluate this. We have our theoretical steam chamber shown here in a homogeneous setting. That's how the theory's been set up. And there's a producer injector. The injection pushes the steam up, mobilizes the oil, basically melts it, and and it, by gravity, draws down to the producer. As soon as we introduce mudstones and shale interbeds, we get irregular steam chambers illustrated here. And this is what it looks like in the simulator if you put these kinds of features. And on 4D seismic, you get a hint of this as well. So the horizontal beds can act as barriers, preventing steam chamber growth, and also local changes in the roof of that steam chamber can cause some flashing. You don't want to have steam going from the injector down to the producer. You want a gradient. And a local low spot can cause a pressure change that affects not only the well pair, but the adjacent well pairs in a producing pad. So we want to know about that too. So to have this communication, we do need the producer to be in the pay zone. And so we also want to evaluate the top, the cap rock, see if it's thick enough and large enough for what its impact is on the steam. So understanding reservoir heterogeneities is key. So we have conceptual flow paths. This is just kind of it's a schematic diagram just to illustrate that you'd have adjacent well pairs and that the steam flows convex, and then we do get some heating, hot plates with conductive heating throughout. So this has been well known for many years. And as SAGD is a base case technology, let's just summarize that only bitumen contacted by steam or high temperatures and able to flow by gravity will be recovered. There are some enhanced techniques out there that can lower that temperature, the mobilization temperature, to some degree. And so we want to, we know that it's an economical process in a homogeneous reservoir. As the heterogeneities get worse and worse, we want to try to understand that. And so here's a rate equation, and the flow rate in that producer is directly related to the length of the producer, or the effective length, how much of that producer is in the pay zone. And so we need to evaluate that. We also have in the flow equation a permeability term. That's very important, vertical perm. And then we have porosity, a saturation type term that's also important because we have a lot of variation in saturation. The height of the net pay is right here, and that's what's quite variable. That's the focus of this talk, really, is on this term. Viscosity is very high to start, and the heating does lower viscosity, increasing this result. And that's the key. So we look at a traditional roadmap for forecasting, and we have our G&G measurements in the subsurface. We compare them to analogs, and we can even look at reservoir behavior in analog fields. But we also do large area mapping, local mapping, and get reservoir properties using wells and mapping. But the key is the 3D modeling right here, going to simulation, getting those performance correlations with the geologic parameters. And so the geomodeling is the focus of the talk here. So we're going to focus on this and some of the key parameters for our studies. Okay, so what are the goals and uses for models in the oil sands? Well, we use them, of course, to input for simulation, but what we're really after here in this presentation is the resource estimates from the static models, not just going to flow. So we want to have some reasonably reliable resource estimates, volumetric estimates from static models. understanding that connectivity. And of course, we can use models for studying hybrid technologies, mitigating risks, optimization of the well configurations, hydraulics, startup studies, and understanding thief zones, pad placement to optimize the drainage of the subsurface. That does come back to the methods we're going to look at. And then placing the wells once we know where our pads are going to be. Understanding the cost, the expense of what we have to inject, and the integrity of the whole system at the top. Do we have a pressure seal, which has been a risk factor? Okay, so there are a lot of uses, but the concepts, we start with concepts. And so here's one of the old concept slides. AAPG 2005. We have the McMurray Formation, we have channel sands. They're large amalgamated channels. The bitumen saturates them. We may have lower zones as well that are smaller. We may have some smaller channel cuts, even mud plug channels. We'll have some top water, top gas. These could be in communication and be thieves. So the continuous bitumen or the continuous pay is illustrated here. We have potential thief. We want to understand cap rock. What is the cap on the reservoir? Both the seal and what's the top of our pay and what's stranded. So then modeling involves these concepts, and so we have the outcrops. I showed you, we visit to understand outcrops. We build our concept models. So here's the channel sands at the base, and these are point bar systems mostly. And then at the top of the point bar sequence, we have these inclined heterolithic strata, which are a sand, silt to silt mud layering that finds upward. That's a typical or a classic situation. We'll use Facies logs. They could be visually interpreted. Electrofacies, I give talks specific to that on building better Facies logs that directly match the petrophysics, provide distinct petrophysics. This is important for the oil sands modeling. Use seismic for the frameworks, integrate the information, build Facies models. This is a dipping one. And we go to the simulator, scale for the simulator. So we're after statistical and physical behaviors. Then we have the modeling workflow, going into a little more detail, slide from Sasan. We have our project, we talk concepts, build the study and framework. We have to create our model zones, set up grids, scale the data into the grids. These are all topics, for more detail, but we're going to focus right here on the geomodel itself. The key part of the geomodel, the heterogeneity modeling, which is hierarchical, the facies, followed by the properties. And there are other parameters I haven't listed here. I don't have listed here. We also use these stochastic models and sometimes scenarios, different scenarios for the model analysis post-processing. So we're trying to summarize statistical information and variation that we might expect in the reservoirs. We're not going to talk about the rescaling and export to simulation or some of these detailed processes. Okay, so the workflow, if we look at it from a different way, there's three parts: the pre-processing or exploratory data analysis in the GNG, using the GNG data, and we mentioned structure, strat, using various information, the facies, petrophysics, and that's where we build 3D facies, and followed by properties. It's hierarchical. Once we get those models, we go look at this post-processing. That's what I call it. Maybe that's from being a geophysicist by background. We use that information and also connectivity calculations, which is the focus of this talk, to rank models based on their connected pay volumes, place wells, simulate scenarios, and look at performance. So we're really trying to make better decisions and feed the economic process. So for permeability models, we have various methods. And I'm jumping across the facies and the porosity. Those are standard. Well, there's some non-standard things we can do with oil sands, but I'm just hitting the big hitter parameters here. So permeability, we could use linear regression. We can go to more sophisticated modeling, but regression off of a good core analysis set can get you a long way. Here it's showing slope of the channel sand, the medium to coarser sands, and it's showing this slope, which is more like the slope here, higher porosity perm, and from the mud shales, the steeper slope, lower poro perm. That's here. So piecewise, with a good linear regression model, you can go a long way. Where it gets a little tricky is with vertical perm, the core plugs. A lot of people don't have enough vertical perm information out of the core plug, and there's bias in the sampling, but you can get some rough estimates, some probability distributions on them. Here with these more detailed studies, what we found with the vertical perm is that as horizontal perm increases in the different facies shown here, or lithotypes, as horizontal perm increases, at some point you get vertical connections in those pores, and the vertical permeability increases rapidly in the better facies. So this shows a very strong percolation effect in the vertical, which we capture through some more detailed studies. And these ideas can be applied back, if you've got this model. This is all dependent on the breakdown of the facies you're using, which is why I emphasize that as an important consideration as well. So then that's permeability. Then we have water saturation modeling, and water, is a behaves physically. We want to understand the vertical trends due to facies, the grain size variation, and capillary effects. So we apply capillarity concepts. And so defining free surfaces is always an issue in conventional and other reservoirs. But we can map bitumen water contacts, in some cases gas contacts are the reference. And so that's a whole discussion on how to find that true contact. There are some tricks depending on which reservoir area you're in. But over smaller areas, you can use TVD. The free surface the contact surface is pretty flat, and that is more adequate than using the stratigraphic correlation in the model grid layers, the K layers. So this using TVD does depend on the surface slope over the area. As the area gets bigger, if you have escarpments, faults, localized faults, it may move. So I've seen it trend quite a lot in some of the larger areas. And it is hard in most of the modeling packages to apply a water contact that's sloping. But you can get the trends, and I'll show you a couple of examples. So here's one where looking at the best sand facies, when we look at the average water saturation, the wells, on the contact, the gas oil contact in this case, we see two slopes here. And what it's showing us is two transition zones. There's this intermediate degraded zone. What's actually a change of environment to a more shallow marine in the upper section. There's actually a transition zone, and that's very well illustrated here. So we use that as a vertical trend in the petrophysical modeling step. That can be done in most of your software packages to find this information. On a large area model like this, it is tricky because the gas, in this case, the contact was sloping. So the facies is shown here. The best facies is the yellow then to orange, and that's highly correlated to, or porosity is highly correlated back to the high quality facies. It looks fairly uniform across here, the porosity, but the water saturation varies laterally and vertically. We see the impact of the transition zone in the upper unit, and we also see the transition zone in the lower unit here. So we want to understand the lateral variation and vertical variation in the saturations. It's important for understanding the bitumen quality. Here's another example, more localized model. We use TVD, and the elevation is from right to left, and that's saturation going up. It's just a big shotgun blast unless you separate by facies and fit these moving average curves through them. For the best sand, the best channel sand, the transition is very sharp, going to the low saturation, to the irreducible. As the sand quality goes down, it's still net in these two. The transition increases and continues to increase in the changing quality, that's changing grain size. And different, you can pick off the irreducible right off of these, the bottom side of the slopes, or the flat spots there. And there is an impact of the top. Some of it has to do with the flattening, and some of it is the degradation of the quality of the sands as we move to the top. So this is also useful to the early development life of the projects. So the transition zone or thief zones may look like this, where you've got the sand porosity shown here in one of the studies, and it shows that you have both low water saturation and high water saturation. If we look just in aggregate at the sand, at the good sands. So this is a good signature of a thief zone, or maybe the beginning of that, like a transition zone effect. So this is a good reason not to co-simulate saturation with porosity or V-shape. Okay, so I'm going to introduce bulk oil weight, talk about it for a bit. And bulk oil weight is the weight percent of bitumen in the mining unit or rock unit. So it's the total bitumen, it's the bitumen weight to the total rock and fluid weight, to the entire rock and fluid weight. This represents a bitumen ore grade. It's the quality. So it turns out that, from the old studies in the late 90s, early 2000s, we saw that bulk oil weight was highly correlated to the steam energy required to mobilize and produce bitumen. So it's a good measure of pay quality for this process. And I'm not sure that's well disseminated in the industry. It is among some of the companies, and I don't know that bulk oil weight's used quite fully in some of the companies. At least that's what I've seen. So bulk oil weight, to calculate it, it's just the density of oil times the saturation of oil times the porosity. So that's 1 minus SW. You've got the grain density. That could be from the bulk density if you want. curve, but it doesn't make much difference, constant versus the density curve. It's 1 minus the porosity, so it's the grain. Then you have the density of oil times porosity times saturation, same over here. Then you have density of water times porosity times 1 minus SO, or that is the SW. So these are added together, so that's the entire volume, the weight of the volume, and the weight of the oil ratio. Okay, and so here we have a table. We calculate that, from constants and the saturation porosity, right? And so a low side for the oil sands reservoirs is 6%. In mining, they use 7% as a cutoff for the blending to go into the processing plants. 7 is usually the bad that is sometimes avoided depending on the clays. But in our oil sands, we look at it at 6% because we're kind of targeting this 50% water as our thief zone. So here it's 48% oil, that'd be 52% water, and that's a 27% porosity, gives you 6%. But there's an ambiguity because you could have high saturation of oil and low porosity. So these are two different cases. This one is a true physical barrier. There's low perm. Here's high perm and high water. 8% up is starting to get okay. 10% is getting into the high quality range. So you could have, you can play with these numbers, but you can have 28% porosity, 77% oil, and the oil can go up in saturation, of course, and gets better. So here's a plot of porosity versus saturation, color-coded by the bulk oil weight calculation. This strong color change here is 6%, so lower porosity and higher water are across that line, and that is masked here in this image. And then notice that this whole section here of high porosity is below 6%, so that's thief zone. It's high porosity to have a high perm, but it's wet. And then over here we use 10% as the cutoff. So this is the 10%, it's the best stuff, the high porosity, low water saturation, high oil saturation. So again, it's high porosity, high water, that's your thief. Okay, so then using this mask of 10%, this is what remains. This is above 10% bulk oil weight. There's low saturation for that 10%, and then there's the cutoff, 10% bulk oil weight on that histogram. Right, so I mentioned that because we showed this graph of the bimodal water, and here's the bimodal bulk oil weight with the 6% cutoff. Right, so now we want to actually plan some pads, some drainage, and we're looking for optimal locations for our wells. So we want to understand these complexities. Okay, so we want to get at the SAGDable oil volumes, and these are the resource producible using thermal gravity sweep, the SAGD based technology. So connectivity is our next topic. We want to understand the connectivity in the reservoir. Where is the steam going to go? In conventional reservoirs, this is an important factor as well. So this in clastics depends on the sands, the proportions, the size of the bodies, orientation, aspect ratio. Depends on your depositional system. Okay, so it's known, it's been studied along the river systems, Mississippi, for example, that as the net to gross ratio, sands to shales, sands to muds, increases, that the connectivity increases quite rapidly in the middle here. So oil sands, what's interesting is that oil sands are high net to gross systems. So the sands are always connected in the main reservoirs. And so we need to know a little more than just the sand connectivity. That's why bulk oil weight comes into play. But the impact is on flow, drainage, flooding, and sweeping the reservoirs. Okay, so here's the statement that the oil sands are high net to gross systems with very high sand connectivity. Conventional connectivity tools do not represent thermal gravity sweep. Conventional tool would be cell-to-cell connections of the net cells. That doesn't work. So we're going to use a mining type approach. And what we're doing then is looking at a criteria for computing net continuous bitumen pay in the model columns. Why model columns? Because that's scalable over from small models to large models. We can calculate this connectivity on large areas for helping us plan our pads and forecast expected production numbers and recovery. And so the other thing is that even though we're looking at columns, any features have a dimension to them just based on depositional concepts. So first, step one is to define the base of the continuous bitumen. And what we're doing, here's a column of bitumen. This is quality shown, in the magnitude here. What we're looking for is a high quality at the base that's thick enough, purely high quality, to put the producer and injector into. So that's needs to be at least 5 meters, and 5 to 7, 8 meters is the target. These aren't completely flat out there, so some tolerance would be needed. I sometimes go down to 5 because of artifacts in the models. So the base quality, we're going to use bulk oil weight greater than 10, so that's a high quality over this thickness. If we have that, then we have a base. Okay, so that's the first step right there. Then the second is the top. So we want to now look for the barriers, baffles. So as long as so now we're going to use the 6% bulk oil weight criterion. Anything less than 2 meters, 6%, for example, it could be 1.5. You could do 3 meters as your non-net. But as long as it's below that thickness that you set, then it's going to keep accumulating, or it's going to keep going up until it gets to a thicker non-net, and that's going to be the top. So that top then defines the gross thickness, and that's top minus base. And then if you remove the non-net, that gives you the net to gross, or the net continuous bitumen pay. So the only problem is this ambiguity about low bulk oil weight. Could be a thief, or it could be a mud or shale barrier. So we want to assess that in the last step. And that we're going to take a look at. We're going to use vertical permeability because that is so important for thermal sweep. So here's your top criteria. It's a seal criteria. You got two cases here. You got top reservoir is going to be low bulk oil weight, low vertical perm, that's top. And here it's going to be low bulk oil weight, high vertical perm, because high porosity, and but it's wet. So looking for a low vertical perm, it'll hit it up here at the top. So you would have one top here based on the low bulk oil weight criteria, and then you get a second top here on low vertical permeability. And the difference then between those two tops is your thief, because steam will actually go up into this zone and reduce the energy. So we also look at this as a block, a lateral block, whereas the other was columns. We need to look at adjacent cells, and we need to look at least 25 meters up to like 50 meters. You could go up to 100 if you want, but you're going to have a hard time in a stochastic model going above 50 and finding something. So we set this thickness to about 1 meter to 1.5 meters, somewhere in there. And so it has to be this entire block of the low vertical perm. And so we're, that's the K barrier. And it depends on what kind of perm model you use as well. So you need to understand where the percolation is, if it's going to be 150 millidarcies, is it 125 or 175? Somewhere in that range usually works for a well-calibrated perm model. So then summarizing with just the graphics, I blocked out the Emerson workflow. It's not exactly, it's not 100%. There's a couple of little logical errors in this diagram. But we calculate the bow on the fly. We identify that high quality body at the bottom. We then look for the cutoff with that minimum thickness on low quality, the non-net, and we get the top. And we assess that ambiguity. So here we'd have porosity, saturation. We calculate bulk oil weight, make the column calculations, might look like this, and then remove the non-net, and that's the net continuous bitumen. The thickness in each column of the cells that are net, this is a binary diagram, zeros and ones, but the thickness of those cells gives us a thickness map here, net continuous bitumen thickness map. And we can use that for some of the pad designs. We can, from the realizations, we can get probability maps, and the P50 is good for pad planning, is a good one to start with for pad planning. But here in a polygon for a pad, we can, take the, the porosity in the net, the saturation in the net, and that thickness, and we get hydrocarbon pore thickness in the net pay and get a distribution. So this would be like a 6-well pair. Pad illustrated here. These are realization numbers and the quantiles, or the probability. So here's the high probability that we'd have a low volume. And we can run, if we choose, we'd run a limited set in the simulator. So the modeling example shown here, dipping beds. This stratigraphy was dipping at 6.5 to 8 degrees and different realizations based on the seismic depths. So we have porosity, saturation, or we could just use a top reference for the Facies simulation, as we'd classically do, and that's shown here. That's discussed in the paper on the slide there. So the post-processing on that one shows us one realization here of a dipping bed. I used 5 meters because, again, some of the artifacts had an impact. So I needed to put this at a minimum. And from that, we can sum the thicknesses and that for all the realizations, and it gives us this textured probability. This is the P50 thickness for the net pay. And we could plan our well on our pad on something like that. This is a small pool. So here's the dipping model, and your modeling choices will impact these results. This is the same workflow except it's non-dipping, shown here. Okay, so the last part of the talk then is just to say that we've identified these areas. We've got this net pay calculation, it's a connectivity calculation for SAGD, and we're going to predict performance without the CPU cost of simulating. Now we do need to simulate for calibration, but what we're doing is running the simulator over the small block area and getting results on it using the different realizations and varying some of these parameters. So we can look at the the geologic parameters would be this net pay thickness, the porosities, vertical perm, saturation, bulk oil weight, and the thicknesses, the net pay, or the even gross pay thickness, net to gross. So from that, we can get the relationship of these descriptive parameters in that pad or even in a well pair in the drainage area. And they would be correlated to what comes out of the simulator here. You can even get it instantaneous numbers as well, at least described in this paper. So this could be run as a fit using quadratics, or it could be run with physical proxies. And again, this paper is focused on the physical proxies. So we calibrate with simulation and the field statistics. We can then use these relationships and use large area mapping, whether it's models or maps, and predict these performance numbers over a large area for planning our development. So this is maybe earlier in the development cycle that we might do this, but we would continue. So then using that idea as well, when we're in a later stage, we can optimize well placement and ranking of well pairs for planning our drilling program to develop and decide on which well pairs to drill first. We want to focus on the lowest risk, highest reward, because we want to maximize our net present value, maximize the upfront economics and return on investment. So we discussed this in 2005, work was actually done in 2003-04, but here we have a map of base continuous bitumen. It's stochastic, it changes, especially away from the controlled wells, and we apply that net pay to the individual model simulations. We extract the base bitumen, and we're looking to place those producers with at least 85% of the producer above this base so that it's in the pay column. So that's a criteria that we evaluated, but I'll just show you if we start with this is FISO on one realization, just illustrating slicing up. Sure, we're going to have a lot of pay above this low level, but the effective length is almost zero. So that's on the realizations, this probability curve of volumes above that level. As we slice upward, we jump up. We've got lower volumes, but better effective length. Finally, the effective length is all in the zone, almost all in the zone, and that's up here. So there's an optimal placement. Again, this one is is a poor location, which makes it interesting to look at, that the effective length doesn't meet the target until you're way up here. So you have a lot of stranded bitumen. That'd be a penalty that we also calculated on the process at the time. And so extracting the P10, 50, 90 curves out of this, as you raise up, the volume, expected volumes, or SAGDable volumes go down. But it's also dependent on effective well length. So again, in the drainage box, we can use those proxy models. This one, I think, used the physical proxy and get the response function. So we input our parameters to model parameters and simulate some of the factors here. We can rank several slots, well pair slots, and then plan to drill out a few other considerations about which ones are adjacent to one another. But this is the key. These are the best ones to drill up front if you're going to drill a limited set of your locations to initialize production. So in conclusion, there are many uses of 3D geomodel simulations in post-processing model realizations. So I've described some of those uses to you. The geomodeling methods are very important for representing heterogeneities, and that's especially true for the, facies modeling, water saturation and permeability for this kind of study. Connectivity is a high impact consideration for thermal gravity sweep. People often do a good job on the permeability and saturation, but connectivity is a more difficult topic in the static models, and that's why I cover this, because I think it's important for people to be aware of these techniques. Bulk oil weight then is a useful proxy for calculating net pay and connectivity, and that's because it is highly correlated to the heat energy needed to mobilize and produce the oil, and accounts for porosity and saturation variations. So the oil sands economics and planning, oil sands economics and planning is enhanced using these post-processing and screening methods. Thank you very much.